introduce Giorgio Metafune from University of Salento, Lecce. He will speak on unified approach to degenerate problems in the half space. Please, Giorgio.
Thank you, Abdel. And of course, thank you to all the organizers for inviting me again here. Now, this is a joint paper with Luigi Negro and Chiara Spina, who are from the same university. And let me introduce immediately the degenerate problems I'm going to speak about. So this is the, I have a window, I don't know if, okay, now it's better for me at least. You see, the problems I'm going to speak about is about generation properties, regularity of elliptic and parabolic problems associated to this kind of operators. So the operators are in the half space, y bigger than 0. The x variable will be finite dimensional in Rn. And with respect to the x variable, we have the Laplacian. But in front of the Laplacian, there is a weight, depending exactly as the distance from the boundary, y equals 0. And on the right-hand side here, then we have an operator acting on the y variable, which is a 1D operator, of course, but it's also degenerate. And for our purposes, it's important that we allow degeneracy. The degeneracy of two types could be in front of the first order derivative, like for a Bessel process, or could be just in front of the potential, like an inverse square potential. In general, both are present, and this we prefer to deal in full generality. And again, there is another weight in front of this normal operator, normal because acts in the normal direction to the half space, which is in general different from the other one. I already said before that if B is 0 here in the L operator, then we have a Bessel operator. And when I use capital B instead of capital L, I have in mind exactly the Bessel operator without potential. Now there are some restriction to numbers alpha 1 and alpha 2, which gives the weights. I see immediately when I say immediately which are these restrictions, but then I will explain later. So we need the alpha 2, this one is less than 2, but also the difference should be less than 2. This is a bit technical, a bit non-technical, but I will comment later. Now, as I said before, script L is a sum of tangential diffusion, y to the power alpha 1 times the Laplacian in x, and a normal diffusion, normal because acts in the y variable, which is normal to the boundary. And of course, there is a complication because they do not commute in general. They commute if and only if one weight is 0, exactly the alpha 1 weight, which is the weight in front of the Laplacian. It's important to note the scaling property of this operator. The scaling is exactly this one. So if we scale with this operator IS, which is a non-isotropic scaling, so we scale with a power in front of x, with linear power in front of y, and another power in front of x. we get exactly this formula. This is elementary computation, of course. And you see immediately that the restrictions appear again. So there is no scaling if alpha 2 is equal to 2, and there is no scaling actually if alpha 1 minus alpha 2. Alpha 2 minus 1 is again equal to 2. Of course, this does not explain the sign y positive. So I mean alpha 2 less than 2 and the same for the other, but at least explains that there is some change when these values are attained. So the aim, as I told before, is to use solvability of the elliptic and parabolic equation associated to script L. And of course, we need some boundary conditions because it's a boundary value problem. We have y equals 0, which is a boundary. We need an initial condition, the parabolic case, and of course, we want to also have the needed regularity, which means either maximal regularity for t and space variables, or even regularity and x and y variable in some weighted Sobolev spaces, as I'm going to explain. Well, I want really to point out some special cases because, well, also the title was a unified approach, so at least I want to show some special cases which we have in mind to unify. This is the easiest case where there are no weights, but still the operator is complicated. I remember last year I gave a talk on this operator in this conference, but of course I do not demand that people remember it. In this case, all complications arise from the degeneracy in the y variable, but there is no weight in front of the Laplacian in X or the Y operator. In this case is also easier because the two operators commute in the X and Y variable. So all generation properties come from free if you know generation property for the degenerate Y operator. Now the second example is when, for example, alpha 1 and alpha 2 are both equal to 1, and let's say there is no potential. This operator is also quite well known. It's a first order degenerate operator at the boundary. It's a model for many degenerate operators, like Baouendi-Grushin, for example, really in the 60s. And in another example, when alpha 2 is 0, so we have only a weight in front of the Laplacian, and this is exactly the Baouendi-Grushin operator, where I didn't put any degeneracy in front of dy, and the potential b over y squared does not appear, but could be added. But just to name the Baouendi-Grushin operator is what I wrote in the last lines. Now, some comments. So the aim is really to give a unified approach to this kind of problems. In the language of semigroup theory, we want to prove that these kind of operators generate a semigroup, an analytic semigroup. Of course, I have to be much more careful about the spaces. We want to characterize the domain as a weighted Sobolev space. This will be, of course, the aim. And also show maximal regularity in the sense that time regularity is separated from space regularity. And now just a first comment. It's quite surprising that the cases where the two weights are equal really are the general case. So imply all other cases by basically by a change of variable, which I know it's elementary and I show now. No, later, so first another slide. So just to say that this is the model case we are going to examine. So we can reduce all the study to alpha 1 equals alpha 2. But now there is a price to be paid, of course. Doing the change of variable, which I have not described yet, one has to pay a price because there is a change in the underlying measure. And this is the reason for which we do not work only with the Lebesgue measure or the symmetrized measure. I didn't say a word, but of course one can choose a measure which symmetrizes the operator and makes it self-adjoint. I will do it later. But I cannot confine to this special case either the Lebesgue measure or the symmetrized measure, because the strategy works if I can work with all these LPM spaces all together. So I need a change of measures to deal with the general situation and mainly to reduce the initial operators to this kind of operators where the degeneracy is equal for the X part, and for the Y and the Y part. And now there are also other tricks which are elementary but quite surprising, I would say, that even for the L operator, one can deal only with the Bessel one, because there is another trick which cancels the potential. This is, of course, much more known because it's very used in the literature, it's widely used. And another trick which also seems to be false, but actually is true, is that the non-boundary conditions imply all other boundary conditions with another trick, of course, and the change of the operator, but this I will not enter really into details because it's only tricky, not complicated. Now the change of variable is just it's elementary again. So instead of unknown u, we use another unknown v called here t of u, which, well, forget about this number, which it's made only to simplify some formulas. We just multiply by y to the power k, and then we make a power change of variables in the y variables. So this change of variable, both of the independent variable and the dependent one, depends on two parameters, the k parameters, which enters like a multiplication, and the y, the real change of independent variable, which is a power change. If you compute, then this t change the measure. It's in isometry between LPM and LPM tilde, and this M tilde is exactly this one. Depends, of course, on M, but on K here, and on beta here, in this way. And of course, beta should be different from -1, otherwise you cannot change. And if you compute, if you compute what happens by similarity to the operator in the first slide, the model operator we have in mind, then there is a change. It's a complicated change, or complicated in the sense that other parameters appear. It's elementary. I'm sorry, because I hit continuously the mouse and then change. And there are formulas which are elementary. So the operator transforms into another operator, you see, with new powers here and here, new numbers hidden in the operator L tilde. And one can play with this beta and k. Usually we set k equals 0, and when we do not have the potential, we play mainly to beta. And playing with beta, one can really reach equality. So the weight in front of the Laplacian can be made equal to the weight in front of the degenerate operator in the y variable. This is the reason for which we can reduce all cases to the case where the two weights are the same. But then you see immediately that this is the point where the change of measure appears, because from LPM we go to LPM tilde. So P is of course preserved, but not M. M is changed. Now, so this is the same comment I was making before. We select beta to have alpha 1 equals to alpha 2, and we select k to reduce to the case where there is no potential, so to the Bessel operator, to the pure Bessel operator, but then the density changes from y to the power m to y to the power m tilde, so we have a weight only in the y variable, as it should be. And we use this strategy also in the case of the symmetrized measure. No, it should be not m equals to c, but m equals to c minus alpha 2, as I wrote below. So there is a misprint there. Now, after this change of variable has been explained, let me say some words about the restriction. So why we need alpha 2 less than 2 and alpha 2 minus alpha 1 less than 2. So let me explain first in the case where the two weights are equal. So the second condition does not appear because alpha 2 minus alpha 1 is 0. And in this case, we only need that alpha, the parameter, is less than 2. Now, let's see what happens when alpha is bigger than 2. If alpha is bigger than 2, this means that we have a strong degeneracy. It's model, well, in terms of the associated process, the process does not reach the boundary equals 0. So that's the main difference. And it turns out that the problem is quite easily treated in the strip. So if we restrict y in 0, 1, at least in the case of the Lebesgue measure. But then there are problems with a strong diffusion at infinity. And this is not done, not yet done. So in the case alpha bigger than 2, the study of the degenerate problem in the infinite strip Rn times 1 infinity requires no new investigation. Even though for the 1D operator everything is quite clear. So putting it together is a problem. And when alpha 2 is different from alpha 1, then a new restriction appears. And this depends on the technique probably we have used. So we use the change of variable with this special beta. And the problem is the following, that the change of variable maps the finite strip Rn times 0, 1 into itself, if and only if the difference is less than 2. Otherwise, there is an inversion with respect to this strip, and the problem is again moved to infinity, and there are exactly the same problems when alpha is bigger than 2 I spoke before. So also in this situation, there are cases where probably one can do something more we have done until now, but some cases really should be understood better, and well, not yet done. I admit this is a bit technical part. Let me point out also another comment, and before entering in some detailed argument, that the range of parameters for which we get generation and so on, as I will explain later, is quite optimal if one parameter, the parameter in front of the Laplacian, is positive. In this case, we have almost sufficient and necessary conditions. Where alpha 1 is negative, there are still some gaps. Now, what is the aim? The aim is to prove this kind of LP elliptic or parabolic estimates. I mean, as is usually done, the LP regularity aims to get regularity in the X and Y variables separately from the regularity of the operator. So this is what is written in equation 1. We want that to control both the X part and the Y part with the operator. And we want to do in the parabolic case the same thing. I mean, separately to control the time derivative and the space derivatives of the operator in terms of the operator. So these are the kind of estimates we want to get. The first is in the half space, and the other one in 0 plus infinity times the half space, because we have the extra t variable. Once one can do this, then one can obtain easily all estimates for the second derivatives separately. You see here all second derivatives with respect to x are collected all together into the Laplacian. But if we want estimates for each pure derivative with respect to the x variable, it's sufficient to apply Calderon-Zygmund estimates with respect to the x variables. The y variable is already contained here. Mixed derivatives, it's more delicate, and I will speak later about them. Of course, these kind of estimates can be also explained in another form. They just say that the operator is closed on the intersection of the domains. So this is the function analytic version of estimate 1, or if you want that this operator is bounded. It's more or less the same thing. And how to do this? Well, the strategy is, of course, to take Fourier transform let me explain the strategy in the model case where the two weights are exactly the same, because we can reduce to this situation as I explained before. If you take script L of u equals f and take Fourier transform with respect to x, you get we get formally this equation here. So you see I already moved the y at the right hand side. So the xi square corresponds to the Fourier transform of the Laplacian. And then we have the operator by applied to the Fourier transform of u. From this formula, we compute what is u hat is exactly the resolvent of by at the point xi square, but applied not the function f hat, but y minus alpha f hat. And then we just multiply by y alpha xi square to get finally this formula here. This is the operator we want to be bounded. F script F stands for the Fourier transform. This operator is bounded if and only if this multiplier is bounded. And this is, of course, it's a vector valued multiplier. Vector in the sense it's an operator valued multiplier, and then we have to use all theory on R boundedness and boundedness of multiplier developed by Lutz, Weiss, its school, and so on. So it's a vector value multiplier because the multiplier is not a function, it's an operator valued. So operator because the resolvent of By appears. So immediately you see that this is the point. This is the main point. We need good estimates for the resolvent of the Bessel operator B. And then there are powers in front, right and left, as you see. So this is exactly the explanation. So we need a Miklin multiplier for this vector valued multiplier. In the case of parabolic one, we take Fourier transform with respect to t, and more or less we do the same. And at this point, one difficulty appears. So I'm just considering regularity until now, but of course there is a problem of solvability for these operators. How to show that such an operator generates a semigroup? So for first one should show that the operator generates a semigroup, then start to investigate about the domain. But there should be at least some abstract way or easy way to show that there is a semigroup generation. And this is not the case in this situation because the operator is not dissipative. So there are a range of parameters, big range of parameters where one aims to prove the result, and the operator can be proved not to be dissipative. And of course, as I very often say, if you cannot prove, cannot use Lumer-Phillips, then you have to prove that the analyticity of you have to prove complex estimates for this resolvent, because I don't see other way. And this is exactly what we do. So we prove solvability checking resolvent estimate for complex lambda. So we prove directly analyticity, holomorphic generation of the holomorphic semigroup by investigating another multiplier. So we get solvability from Miklin theorem again. But in this case, of course, we need another parameter lambda. The spectral parameter lambda should be used because we want to show that this equation has solution. So this is the multiplier connected with solvability. And then we have to prove the right decay in lambda. So should decay like modulus lambda with -1 to get the resolvent estimate. And this is what we do all together. Now, let me say, after this very, very long introduction, which is really the main part of the talk, some technical tools, how to start with this operator, how to prove that this operator really do generate something at least easily in the L2 situation. So this is the maybe in a paper is page 1, where we start with, we give a meaning to the operator. So the title of this section is the operator. You see y alpha delta x plus y alpha by. There is an n, an upscript n, which means that we are considering Neumann boundary conditions in this slide. And now in L2, which is the easiest way to deal with, and the weight is C minus alpha. So we weight the measure with y to the power C minus alpha. And the reason it's easily explained, this is the symmetrized measure for the operator. And the operator in this space corresponds to this form AUV I already indicated before. So, so this is the form with form domain H1, which depends on two parameters, alpha and C again. So this is the inner product in H1. This is the form, the operator, it's easily seen to be, the form is easily seen to be closed and positive definite, so it defines a self-adjoint operator. So at least in L2 with parameter C of alpha, we have a self-adjoint operator, and all generation properties are settled easily, and the form domain, it should be a Sobolev space of first order. It's H1 with parameters alpha and C. Let me go on. Now, we don't want to stop to the form domain, but we want to go directly to the full domain of the operator. Even in L2, we have to do that. It's not obvious how to do. And now let me introduce in general the Sobolev spaces we are going to use. Sobolev spaces are functions, consist of functions in W2P of the half space, for which the function U, and you see pure second derivatives with respect to the x variables with the same weight which appears in the operator in front of the Laplacian, should be in LPM, and the same, but with the other weight, sorry, y to the power alpha 2 dyyu should be in LPM. So this is, I would say, the right Sobolev space model on the operator, because contains exactly the anisotropic parts as they are in the operator, exactly with the same powers. To be short, I didn't say any word on first order derivatives. They are not the main point, because the integration properties of first order derivatives depends on the follow from interpolation, by interpolation. So one expects that if U and y to the power alpha 1 dxixju is in LP, then for the first derivative, I mean the gradient with respect to x of U, the right power should be just half between, so the mean. And in fact, it's what happens. So we prove that y to the power alpha 1 divided by 2 times the gradient of U is in LPM, and the same for y to the power alpha 2 divided by 2 dyu. It's in LPM. And I don't say any word about the mixed derivatives because it's more complicated than I will say later. And then the boundary condition. The boundary condition, it's written in this way. So we divided by an extra y. So it's we are saying in a sense that dyu over y, it's in the weighted Sobolev space. So it's this forces, in a sense, at least when alpha 2 is 0, that dyu is 0 at the boundary. And this formulation, it's more or less equivalent when there is when can give a meaning to the trace of boundary, of course, using hard inequalities. So it's saying that du is 0 at the boundary, it's more or less equivalent that dyu of y, it's integrable in LP. And let me point out also that all formal computations I did before with the Fourier transform become really true computations if one can identify a good core of smooth functions. And this is the core we use continuously in the paper. So we take functions which are tensor products is in the last line of functions, smooth functions in the x variable, smooth functions in the y variable, which are constant in a neighborhood of the boundary. You see, we impose that the y derivative is 0 near y equals 0. So the function are constant of y. And this, of course, resemble of the Neumann boundary condition. This is what we prove. So this space is dense in W to P if this condition is satisfied. So M plus 1 over P is bigger than the negative part than alpha 1. And this is necessarily sufficient because otherwise the space we want to prove to be dense is even not contained. And well, if we assume now in the next result that the parameters C plus 1 is bigger than the modulus of alpha, it turns out that the domain is what should be. So it's a Sobolev space of second order, and these are the right parameters. I know that's a bit technical and one gets lost after a while, but unfortunately I don't see any easier way to present. The parameters say, this only say that alpha 1, alpha 2 is alpha, and the weight is C minus alpha. And also in this case, to prove that this is the domain, we have to use the boundedness of the multiplier I said before. But the boundedness in this case, of course, it's easier because we are in L2. So boundedness of multiplier is equivalent to boundedness of the vector value function. So in L2, everything is easier, but again, the strategy is in any case to use the Fourier transform. Then we want to extend these results in LPM. So go away from 2 and change the measure, also because the change of measure is essential to deal with all cases. Well, and this is the main point. This is the main point. The main point is summarized in the next lemma. Under suitable condition, the parameters. These conditions are precise if alpha is positive. So this condition becomes really necessary, even if alpha is positive. If alpha is negative, there is some gap. Then the main point is that if we consider the operator constructed in L2, what I indicate by script L with index C minus alpha. So just to distinguish, because now we have many spaces and we have to distinguish between the operators. If we consider the operators constructed with the L2 theory, so the resolvent, and the two operators which gives the domain, so y alpha times the Laplacian multiplied by the resolvent, and the next is similar. These operators are well defined in L2 and bounded in L2 because of the L2 results. Well, they actually are bounded in LPM. And also, if I multiply this resolvent in LPM by lambda, this is R-bounded, which means Rademacher bounded, so satisfies square function estimates in LPM, which is essential for us for using Miklin. And this is the main point. So it says that L2 theory extends to the LP theory. And of course, this relies on Miklin because we have to, we use Miklin to prove this lemma, which is the basic lemma. And having that, one can construct a resolvent in LP using pseudo-resolvent, using basically the resolvent in L2, define an operator, and finally show that the domain of this operator is the Sobolev space W2P with the Neumann condition N, explained before. As I said before, the condition in the statement about numbers, so the negative part of alpha should be less than n plus 1 divided by p less than c plus 1 minus alpha, is necessary and sufficient when alpha is positive, because corresponds to the generation property of the Bessel operator, y alpha times b. When alpha is negative, well, there are some gaps, but I would say it's quite, but at least it's necessary for the description of the domain. It's not necessary for generation property. So there are cases where the operator could be a generator without having this description of the domain. Let me go. Now, one point which is usually a headache in this theory, I never inserted the mixed derivatives in the definition of the Sobolev spaces because it's easier not to insert. But then it turns out that they are really present, because under the same hypothesis that I had before for the generation theorem, then one can bound the mixed derivatives of the solution with the operator. And of course, one can wonder, but if this is a property of the operator or it's a property of the Sobolev space, at this level, these two questions are really equivalent, because the domain of the operator is exactly the Sobolev space. And we tried to give a self-contained, a pure Sobolev space proof that from the existence of pure derivatives with respect to x and y, one could deduce the existence of the mixed derivative. But I should admit that I cannot do even for classical Sobolev spaces without using the Laplacian, let's say. If I use the Laplacian, if I know that in two variables, uxx is in LP and uyy is in LP, then the Laplacian of u is in LP, and by elliptic regularity, the mixed derivative uxy is in LP. But then I have to use, let's say, Calderon-Zygmunt results for regularity of the Laplacian. This is exactly what we do. I do not have direct proof of this without using the operator. And so, for example, I don't know if the result is true if I do not put a Neumann boundary condition, pure I mean at the level of Sobolev space, not at the level of the operator. Now, for the end, what happens in the general case? We have only to translate at this point, because the problem is completely solved in the alpha 1 equal to alpha 2 case. We translate with the change of variable way I explained in the first slides, and this is the final result written in the theorem. If the alpha 2 minus alpha 1 is less than 2, and also alpha 2 should be less than 2, I forgot to write, then we have generation of holomorphic semigroup with maximal regularity, and the domain, it's the Sobolev space one has in mind, one really things should be. Also some words about Dirichlet boundary conditions. I spoke only about Neumann, but one can do similar with Dirichlet, but better, one can reduce Dirichlet to boundary condition to Neumann, playing again with the change of variable t, but this time playing with the parameter k. Playing with k, one can translate the results for Neumann boundary condition to Dirichlet boundary condition. This seems to be wrong because one says how to do this for the Laplacian, for example, how to deduce Dirichlet for Neumann, but can be done because the change of variable k changes the operator. So if you apply this trick to the Laplacian, you change the operator and then go to a degenerate operator. So it's of course more complicated this way to do for non-degenerate ones. But in this theory where all operators are bad altogether, to get another degenerate operator is really not a problem because you start from a degenerate one. So in this case, Dirichlet boundary condition can be treated. There are quite precise results. Again, I do not list because the situation is a bit confused. Also, there are many other conditions. In some cases, even necessary and sufficient, but I prefer not to list all. The only thing which should be said is usually with Dirichlet boundary conditions, the domain is a bit less regular than the Sobolev space I mentioned before. This is more a curiosity, but it's interesting to also to mention. I think I have 2 or 3 minutes still. Dissipativity. I mentioned several times that there is a problem to show generation for these operators because there is a lack of dissipativity. And this is the situation. So one sees quite easily that dissipativity depends only on the degenerate operator y. So the Laplacian is dissipative, there is in X is no problem. So everything depends on B. On By. And also one can reduce to the situation where y to alpha 2 is 1, so when alpha 2 is 0. So the only thing which should be investigated is the dissipativity of Bn in LP, and the situation is the following. Either M is C, so it's the symmetrized measure, or M should be bigger than 1, and this other condition is satisfied. This is, I think, a bit strange to guess without doing the computations. One easily guess that in case I, so when M is the symmetrized measure, then the operator is dissipative, so because it's quite clear, because in L2 it is clearly dissipative, it's associated to a form, and then Berlin-Denny condition hold without many difficulties in the symmetrized case. But then to see that there is another and only one another situation, it's more tricky. So let me just say what we obtained. For example, you see, in the case of Baouendi-Grushin operator, we obtain the domain. I just wrote down what happens in the easiest case where it's really the classical Baouendi-Grushin operator. We obtained these results, which we already proved with Chiara and Luigi, but 2-3 years ago, but only for positive alpha. Now we can really reach some Mackenout classes for alpha, so we can do for alpha negative, some negativity it's a load. The methods are different, of course. And you see, for example, I point out in this case what happens also for the mixed derivatives. You see, in the domain, the y derivative is without alpha because the operator there is no alpha with respect to y. There is y to the power alpha in front of the second derivatives pure in the x variable, and alpha over 2 for the mixed derivatives, as should be. This is another popular example I mentioned before. So first order degeneracy, again, we have a description of the domain. These results in the first order degeneracy were already known. For example, many years ago with Jan Proust, we proved similar results. Then Jan alone filled a gap in some range of parameters. And Koch also in this habilitation thesis proved in some range of parameters similar results. And now we found altogether these results from this theory. And well, just the last slide for who is interested in this theory of multipliers. This is really the last slide, so a comment on the main tool. There is a nice formula which we used several times. So I really wrote down the two main multipliers we have to use. The first multiplier at M is for the domain. The second multiplier is for generation. They both depend on two parameters. So lambda is a spectral parameter which is connected to solvability, and psi, it's the spectral parameter connected with the Laplacian. If you take the Fourier transform, the Laplacian becomes equivalent to the multiplication by psi square. So the role in principle of these two multipliers is different. Lambda is a solvability parameter, psi is it's a spectral parameter after taking the Fourier transform. But they are connected in the last formula. If you see the last formula, this formula, it's easily verified formally. If you take a compute, you see that this formula is verified, but justification requires really some effort. You see in this formula the role of psi, which is now denoted by mu, sorry, bar is missing here. The role of mu and lambda is changed. Here mu is a spectral parameter and lambda becomes a part of the potential. And here it's exactly the contrary. So lambda is a spectral parameter and mu becomes part of the potential. And this nice formula allows really to treat lambda and psi square both as spectral parameter, because one can shift from one to the other just using this formula. So I think I finished also a bit over time, so thank you for all.
Thank you very much.